I first wanted to say that I very much enjoyed your talks yesterday night. Very interesting. And that brought me to a remark, maybe I should have said yesterday because there were more people. There's an application of random matrices to Wilson groups in anything called superunion. And the paper I just wanted to mention to you in case you are interested is by David Gross and Gernot. So what they did, they didn't look at a Wilson loop with a cusp as you saw in the talks yesterday, but they looked at circular Wilson loops, and they used actually a matrix model to count all planar non-intersecting diagrams. So the paper is TH. Number 074. So if you're interested in the details, so basically what they showed is that due to the gauge, they chose the propagators became constants. So it was just a counting problem as we have in the matrix model. And in fact, the object they had to evaluate was an expectation value of the trace of this exponential that you can get actually by Laplace transforming the resolvent, which they didn't know, but they didn't need to know. And the weight function was just where lambda is the top coupling. So they did a counting problem using random matrices. Of course, then you have to show that you only need planar ladder diagrams, and I think it was shown at least to a certain order of loops that higher order contributions cancel. So that was that is another application of random matrices, but I will not talk about this any further. So let's go back. So we are at the moment at computing not these objects, but we are computing resolvents. And we use a very general wave function. Then you put the n here, trace h. And what we showed is that if we do an expansion around with n equals infinity, then we get what is called a loop equation. So we assume that all the eigenvalues of the matrix H will condense on some finite interval or more than one intervals. And then we got the following equation. Okay, so this is the loop equation, and this you can also write as 2-point correlator, so that's the same thing, inserting two traces of this object, or just putting a square here and then taking the connected part. And this derivative is just generating this object, but I like to write things in this fashion because then you see it's really an equation that only depends on the resolved W. Now what we also did yesterday was we solved this loop equation in the planar limit. So this is the planar loop equation. So g is equal to 0. So then if I drop this term, I can put 0 everywhere here. And the answer that we got was following. Let me write this down again. And maybe I should have reminded you where this contour contour runs around, in this case, the single support of the eigenvalues in the larger limit. And the only things we don't know in this solution here is the endpoints of the support. I hope you can see that. So that's the bound of the interval A and B. And I still need to tell you how to determine these in terms of the coupling constants in the potential. And then everything is fixed. Okay? But before doing that, I would like to do an example. Namely the example we started with, also because it's early in the morning, so it's good to have a simple warm-up exercise. So, okay, so how do we compute this? Now, when I write it in this form, I put everything in one integral. I could have also written these here in an equivalent way. That is the following. Okay, and then so this is potential. Now, in this case, we have just degree 2. And this is a polynomial that depends on D. And was given by the following expression. Okay. Now we also convinced ourselves that this polynomial, just by counting when we had solved this quadratic equation, the degrees, that this polynomial is of degree d minus 2. So for the Gaussian potential, obviously this is a constant, and that's what we expect. But let's check that this indeed comes out. And so what we need to do for that, so we just have, this is of order, this is just omega, okay? So here, so we have omega, and then you basically have to play the same trick always doing residue theorem. We do it at infinity, but you can map that to the origin. So all we need to find is to pick the contribution to the pole 1 over omega. So you see this is an omega. If I take omega large, this gives another omega. This gives a third omega. So this will give following. Okay, so you see that this is indeed 1. Okay. So the only thing that remains is that we have to determine A and B. Now, this potential is symmetric, so life is a bit easier here. So from that we can infer that B. And then all we still have to check is that because this is defined in this fashion and this goes like 1 over p for p going to infinity, which is of order 1. So also W0 goes like 1 over p for p goes to infinity. So this should go like 1 over p plus order, in fact, 1 over p cubed. So let's check that. So here we have 1/2 p minus 1 times p times 1 minus a over p squared 1/2. Okay, now you see, aha, that's nice because this will, the p's will cancel as it should. This 1 minus 1/2 p squared. So then you see that these cancel, you get a plus 1/4. So this has to be of order 1. So then implies a. Okay, so let me write down the result for the resultant for the Gaussian model. Make a function in the complex plane. 1/4. Okay, now.
Sorry.
Yes.
Could you please repeat it? I missed a couple of points. Why is a equals minus b equals symmetric, and why we expect 1 over p? I know it's trivial questions, but I missed.
No. Not a problem. So you agree that from this relation we have that the resolvent taken at very large p has to
Okay.
be like 1 over p.
Fine.
Okay. And then you just compare that to the expression that we calculated to make an expansion also for p large. Just expand this gravity.
Yeah. Okay.
The first terms cancel, and then all that remains is a square over 4 divided by p. So a square over 4 has to be 1. That's it. Other questions? Okay, so we have now computed the resolvent, and if you remember in the very first lecture, I started out with this matrix model here, and I claimed that the limiting spectral density is a semicircle. So now we still have to find a relation between these two, and that is in the notes, but let me of course write this down again. So from the definition here, that W not P is lambda rho of lambda P minus lambda for P not in the support. So in this case, not in the interval minus 2, 2. We can read off the expression for the density. So this is for general potential, of course, and the relation between W and rho also follows easily from complex analysis. So let me write it down. So it's basically taken the imaginary part of W and divided by pi so that the density is normalized to 1. So, well, you can see that here that, in general, the resolvent is a polynomial minus another polynomial times the square root. So what we do here is we just take, so this is a b, obviously because as a function in the complex plane, this has a square root cut. So the function has a jump. You compare the two values from up and down, and this jump just gives you the density. That's what it says. And well, it's imaginary because, well, you see that for lambda in AB, you just have lambda minus A, lambda minus B is of course I times B minus lambda A minus lambda. So this is now positive. And because it's described in the complex plane, you will have a different sign from here and from here. Okay. So in our particular case for a Gaussian potential, we have that rho of lambda is just the discontinuity of this object here divided by pi. So we just get 1 over 2 pi square root of 4 minus lambda. And this is the celebrated semicircle. Of course, you can derive the semicircle much easier than we did, but this is just the first example I wanted to give to you. Okay. Nobody asked me why I write Gauss in this way. Suppose you're all fluent with German language and you can make the plural of Ansatz, which is Ansätze. Well, Friedrich Gauss, I think this is the German sharp S, and this is how it traditionally spelled. And if you want to know more about him, there's a very nice book by Akemann. I think the English title is called Measuring the World, and it's a double biography of Friedrich Gauss and Alexander von Humboldt. They also meet in this book, so it's great fun to read. Okay, so going from Gauss to something more non-trivial, let me give you another example, which is not more complicated in this case, actually, and that is the example of chaotic potential. No, before I want to do that example, I still owe you the relationship between the potential and these endpoints A and B. Okay, I mean here I just did some little calculation, they came out, I was happy. But in general, this can be made a bit more formal, and but the idea is basically the same as we use there. So we have that on the one hand side, so the relation endpoints A B in this case, and B P. So we have this is equal to 1 over P plus order 1 over P squared. And on the other hand, we have the solution which I just erased. So I can spell that out. So so what did we have? We had a square root containing p's and a 1 over omega minus 1 over p minus omega. So everything gets expanded now that depends on p. So let me copy everything that does not depend on p. So we have to expand. Okay, let me write this down in more detail. So what we need is we need p times 1 minus a over p, 1 p over p 1/2 divided by p 1 minus omega over p. Okay, so these cancel, and then you just multiply this out. So for this vector here, you get the following: 1 plus 1 over 2 times omega minus 1/2 a plus b plus order 1 over p squared. So you know that this integral over the constant part should vanish. Okay, so that gives us one condition. So 1/2 omega 2 pi r d prime of omega square root omega minus a omega minus b times 1. This should give 0. This is this term. Now, because of that, also this will vanish, this integral, because there's no omega here. Okay. So then the integral over this term should give 1. Okay. So let me write this in the following way. K delta K1 okay is 1 and 0. Okay. Now these are two equations, and they determine the f. Okay. So far, so good. So now comes another example, namely the quartic example. So basically, the computation will be very similar. Okay, so example 2 plus g. Okay, we can also put a coupling here. Let's put that G2 and G4. This is how we did it. This remains the same. Now this now here has omega G2 plus G4 omega cubed. Okay, so you see that we have to expand things a bit further, and when you do that, maybe I don't need to do that. What you will find is that first of all, this is a polynomial of degree 4. So this was a polynomial of degree d minus 2. So this should be a polynomial of degree 2. And when you do the calculation, I mean, it's not difficult. I mean, you just expand this out, and positive powers of omega vanish due to residue theorem. Negative powers vanish except the power of 1 over omega. Okay. So what you get is the following. So polynomial of degree 2, and this is what we get, plus 4 times p squared minus b squared. So let me write now the full answer, because this is something very nice. Minus, now comes this polynomial, G2 plus G4 p squared plus a squared over 2. And of course, this is again even, so again, our boundary points come out to be the same. So this is the equation for the resolvent. The density, then you can read off immediately, it's just 2 over pi times this. This is the density. This again the discontinuity. So for the density, you don't need the polynomial part. And the last step is to compute the equation for the endpoints as functions. For we have 2 endpoints, but of course they are now symmetric. This is square missing. And well, you can see already that okay, this will drop out. If you do this, I mean, I'm not doing this calculation because you know I've seen it many times. You plug in the potential, you expand everything. This you can deform to infinity, because once you have expanded it, there's no pole at P anymore, so this contour can be pulled to infinity. Then you expand this at infinity, you do residue calculation, etc. So these equations that we call star, so capital 0 is identically satisfied because potential is even upon k is 1, you get the following equation. 1 equals 1 over 4 2a squared plus 3 over 16 4. So these two equations together now determine everything you want to know about the quartic potential in the planar limit. Okay, so this is everything. We have the resolvent, the density, and an equation. Now I should say that there are also more possibilities. I mean, if you draw the potential, depending on the couplings, if they are both positive, the potential will be convex. But if you choose G2 to be negative, that is perfectly possible. You get a Mexican hat, and then you will expect that the eigenvalues will lie in not one interval, but two intervals, depending on the height of this barrier here. So for this potential, we can also have a two-cut solution. Okay. So then sigma will be minus d minus a. Now let's have a look at what we have to modify then here in our approach. So I think I already told you last time that we have to make an ansatz here where we have here the 4 factors that do not get pulled out of the square root. Our support then looks as follows. And what I just erased, of course, remains valid. Okay, so this is now sigma. Our contour, well, first of all, our P in the solution of the loop equation, this one here. One can show that this will be of the same structure, so this pole remains, this square root will be a square root of 4 factors, this will be a square root of 4 factors. I think you see it. And the contour will avoid the point P, that is the union of these two. Okay, now we have 4 endpoints, and so we need 4 equations to determine the solution here. And the 4 equations, well, how do we get them? We again have to satisfy this here. Now, of course, the expansion will be a little different because now we have 4 square roots here that we need to expand. So what will happen is, so for S cuts, we have S2 as parameters. A, R, 1, 2, S. Now, if you write down everything, you will find that this equation here gets modified to the following equation. Yes, I'm not mistaken. I'll just check. Yes. Okay. And so you will say, aha, but this only gives S plus 1 equations. So we are missing something here, and that was solved, well, there are 2 ways to solve this. Now, one way of solving this is to say how I take the larger limit. I take it in the way that I fix fractions on these intervals. So we have, let's say, intervals 1 to s. So n my 1 to s. This should be n. So we have n minus s minus 1 fractions that are free. And the other possibility to fix this is to require that in the larger limit you get an equilibrium of chemical potential. This was proposed in a work by Kiewicz. And that gives rise to, actually that can be written in terms of the following equations. So sigma I bar is, these are called sigma 1 to sigma s. Then the complement here would be this one, if we integrate over this times m times the square root from 1 to s lambda minus I. This gives the remaining s minus 1 equations. And if you want to know more about it, you should look in this paper. Which was my PhD thesis, so quite some time ago. Okay, so why do I tell that? Because if you remember last time, we were
Gernot,
yes?
just but these equations are sort of answers that when also can be derived from first principle.
Well, you think about this that, well, how does the larger limit occur? And you think that for finite n, you have, you have this n-dimensional integral for the partition function, and then eigenvalues can try to equilibrate by tunneling, and that is why you think about posing this condition. Actually, this is not the whole story. I was going to mention that later, but so these solutions that we are just about to calculate for the quartic potential, these are called multicut because the resolver now has several cuts in the complex plane, and this discussion of the larger limit in this multicut situation is more subtle. So it turns out that yes, this is the smooth contribution in the genus expansion, but there are actually non-perturbative terms that occur due to the nature that, well, you have an integer number of eigenvalues. And these non-perturbative terms, they've been computed in a paper by my colleagues from Saclay, which you can find here. So you see some of the random matrix model literature is in Coulomb, or was in Coulomb, now mostly on matrices. So they show that you get some non-perturbative contributions that involve Jacobi theta functions. So these are non-periodic contributions. If you like, they are something that you get in addition. I should also say that these multicut models then became popular again, I think, in the late 90s. Works by Dijkgraaf and Baffa, where they related these to supersymmetric gauge theories and the scope potentials. Okay, but let's get back and let's get a bit more down to earth. So I mean, we want to compute these solutions because, as I told you, we are interested in making this relation to conform with Field. So we want that these higher genus contributions to the free energy, they appear in what I call double scaling limit. So we want to find some critical points. And the critical points we were after were points where, for example, the spectral density does not vanish like a square root, as here in the sine term in the semicircle, which are raised. Also here we have the square root, but we want this to vanish like also 3/2. And now we see with this model, we can actually reach this critical point. Okay, so let's look how it goes. Well, it's very easy. I mean, we want that the density vanishes like T minus T squared. Okay, so this is the density. So all you have to do is you have to fine tune your couplings G2 and G4 such that this behaves like P squared minus A squared. Okay. And it's a simple exercise given this and this equation that this critical point happens when so G4 critical is minus 1/12 G2. So that you still have rescaling degree of freedom, of course. In your matrix model potential, I mean, as we scale out a factor of n, you can overscale out one factor. So, in fact, we don't have two couplings in this quartic model, we have just one, as you can see. So, this is the first example for multicritical point. And, of course, I still have to go to higher genus contributions that we will also do. Of course, we will not get all the way because the paper by Ambion and co-workers that I gave you the reference, well, it's a long paper and you have to do some calculations, but I will show you what the steps are and we will arrive at least at the genus 1 free energy later today. Okay, so this is one possibility of having critical points, and now it's somehow clear what happens. I mean, if I would take a higher order potential, I get a higher order polynomial here, I get a higher order polynomial here, and it's clear that I can then get here higher powers, 5.5, 7.5, etc. Okay. And in fact, these are all the multicritical points that you can reach for general V. So, general V, so the critical points like this, 1.5 plus n. Okay, I think this you can see now. What you cannot see that these are the only critical points we get at the endpoints for polynomial potentials. Now this is one thing. Then again, you can ask. I was advertising something called universality. So now suppose we take not the quartic potential, but we add a sextic term. Okay, so we get a higher order polynomial here. Here we get then a polynomial of degree 4. Now, of course, we can tune this just to develop one extra zero at the endpoint. So we get 3.5. So then we have one more free parameter, and the claim is that this will be in the same universality class of the multicritical point. So also at the multicritical points, we can have universality because we can have a whole family of potentials that give rise to the same critical point. Now, let me write down the two-cut solution now, because I would like to illustrate another type of criticality that you can have in these one-matrix models. Okay, so two-cut solution. So it's almost written here. So now what we get two more roots here. So that means we reduce the degree of this polynomial by 1. So this now has e minus 3, which is 1. And because of symmetry, this will just linear and not have a constant term. So this solution, if you spell everything out, is the following. Minus 4p t squared minus a squared t squared minus b squared. Okay, and for the endpoints, I don't think I give the relation here. But okay, you can write this down. So, questions, can we have more critical points? And the answer is, of course, yes. Now, what can happen? Well, it can happen that we tune our couplings such that these two cuts will merge. Okay? So what will happen then is that our density that initially looked like this will go to something like this. And of course we could also reach that here, namely, so again, this is the density. Now, because of symmetry, we have an even potential. This point will happen at the origin. So let's call this also one-part density. Well, I didn't write it down. So you can see this happens at the origin. So when will this happen? This will happen when this plus that is 0. Because then the density at the origin will go like t squared. Okay, so this will go like lambda squared. And the same thing here. I mean, when a goes to 0, you can pull this out, so the density has a vanishing like a square. Okay, I think this you can see very clearly. Now, it turns out that for general potential B, what you can get is this. You cannot get other critical points than that. Okay, and then you may also want to know what is the order of this phase transition. Typically, it's the third order phase transition. So the third derivative of the free energy is discontinuous. Physics, mostly you are encounter first and second order, but for these kind of critical behaviors, you don't get first or second order.
Would it be different if you had a 6
No.
potential and you tune to 0
No.
G4?
You can then get here lambda to the 4, lambda square. You can get here 3/2 and 5/2. You cannot get anything else, and the order of the phase transition will also be third order. If you want to get
also be first order?
No, third order.
Third,
Always
sorry, yeah.
third order. So, so both this is third order, and this is also third order. Now, if you want to do something that has a first order transition or second order, you have to modify the potential. You have to put here something non-polynomial, or you can add an external field, then you get a first order transition. This can also be done also using loop equations, but I don't have time to do that in this course. Okay, so these are the possibilities for critical behavior. And I would now like to continue, if you don't have any questions, to try to compute now higher order contributions. So this was W0. Yeah. One thing I should also mention is, I mean, you see that W0 and the spectral density, they are non-universal quantities. Why? Because when I add here static potential, I get more terms. So this all depends very explicitly on all couplings. And it will change if I add more couplings. However, we will see that the higher genus contributions to the resolvent and the free energy are universal. So they will, will be able to write them in terms of few parameters, few meaning 1, 2, 3, 4, for arbitrary polynomial potentials. And those will be universal quantities. This is quite surprising in a way, because as you will see now, we set up a recursive relation to solve for higher genus contributions of the resolvent, and the starting point is something non-universal. But then when we go on, we get something universal, and it's quite amazing to see. Okay, so how do we go about? Now, maybe I should remind you of the loop equation, because now we are going to solve this iteratively. Here we go. Okay. So, so what do we do? We now insert genus expansion. So W is 0 to infinity, and minus to G, W to P, and likewise for point correlation. So insert that here, and then we just compare order by order in genus. Okay, so the first term we need is this term here. We need to do a little bit of multiplication, so you can show that the following is true. Or you just square that, and then you get a double sum, and then you use the Cauchy identity so that you can write the product of two infinite sums as one infinite sum times a finite sum in the following way. You can all do 0 to G Okay, this is not difficult. Okay. Are you still with me? Okay. Now, so we plug this in. Sorry, I'm missing here the minus, of course. So I plug this in here in the integral, then I plug this in here. Of course, this will shift n by 1, and then I plug in this here. What do I get? Well, as I said, we want to do something recursively. So let's put everything that depends on, let's say at the starting point that depends on genus 0 on the left-hand side and everything at higher genus on the right-hand side. So now if you look at this sum here, this sum will have one term that is the lower part W0 of P, W G of P, when G is 0, G prime is 0, and also when it is G. Okay, so we get twice this term from this side. So let's put this on the other side. And then we get the following object. will write say what I write in a moment. Plus, okay, I can write it in this way. Okay, so on the right hand side we have terms that go from genus 1 up to genus G minus 1. Okay. And on the left hand side we have this thing here where this object K is an integral operator that just involves this contour integral. So I've done nothing fancy here. Okay. So how do I read this equation? Maybe I write down the simplest example for genus 1, and then you see what happens. So genus 1, I have K hat minus 2 genus 0, acting on W1 P is giving me on the right hand side W0. So the right hand side we know, we still have to calculate it, but we know it in principle. And then the left hand side contains what we want to compute. So all we have to do is we have to invert this integral operator. Okay. So the integral operator is given by this, minus 2 times something we know. Now it turns out that the right hand side will have will be a rational function in P minus A and P minus B. So we will find a basis for this operator acting on basis functions that give rational functions. So once we know the left-hand side, write it as a rational function, we can invert this operator to get genus 1. Then, next step, we want to get genus 2. We have the same operator acting on genus 2. On the right-hand side, you get genus 1 and genus 0, I think. Yes. Okay, so then you plug in what you know on the right-hand side, you solve for genus 2, and so on and so forth. And it turns out that you always need the same set of basis functions because they will do the equation. This is what was done in this paper by Ampion et al. For general potential. So let me give the reference again and give you maybe some details. So, invert K hat minus 2 P. And how do we do that? We find a basis that we call that phi A P n. That gives 1 over P minus A to the n and similar B. We didn't need A and B for the one-cut solution so far because we only had 2 examples that were symmetric. But in general, the endpoints are not symmetric, not be symmetric, so we need these 2 sets of basis functions. And then So we will get from this W0, this is a rational function. Invert k at minus 2 not, and then we get W1. And then again we get W1 of p comma p. By doing this differentiation, put here g is 1 square, writing it as a rational function, invert the operator. Okay. Now this procedure was also made a bit more efficient by some people like Gernot and Nicolas Antin. I will not give their prescription because I think this is going too far. I just want to do genus 1 and give you an idea how this works, and then I will not be able to give more details because otherwise I would spend all my lectures only on this particular point. So, now one question you could ask here is, can I always do this inversion of this operator? And the answer is yes, for one cut. So this has a non-trivial kernel. So the kernel of this operator is something that gets projected to 0. Now for one cut, it does not have a kernel, but for more than 2 cuts, one has to worry about that, but that can also be fixed, and then this inversion can be made possible. Okay. So now I was talking about universality before, so I still need to introduce one ingredient, and that is the following. So maybe I should put here the reference again. My and co-workers, and they have a series of papers, and in this paper basically the full power of the machinery is there. So what they propose is to change from the coupling constants in terms of which we have so far determined everything to new sets of parameters, namely the endpoints, in something they call moments, A and B. Okay. And the universality statement will then be an arbitrary potential, so even with an infinite set of couplings, I will at every genus only have a finite set of moments that enter the correlation functions. So in that sense, the correlation functions will be universal. So let me write down what these moments are. So basically they are, again, very similar objects. So if you have the square root here, and then you put here another part. So these are the case moment for A and for B. You just okay. And then the universality statement is the following. So for any genus, they show through this iteration 1 to G. where this is the number. So the genus 0 resolvent depends only on up to so many moments for example, this can be M2 over M1 or M2 over M1 squared. Now you already see in a way how then these multicritical points will be reached, namely this will be reached when these moments will start to diverge with some power. So then these higher genus resolvents will diverge, and then you can also compute the free energy by the following integration. That is a non-trivial step actually. And Akemann and co-workers, they managed to do this integration, so you have to get this, and then you have to, in a way, guess how you can write this as a derivative, and then give the free energy. Okay. I think what I would like to do now is to give you some idea how to go through this problem, or maybe I skip this actually. So maybe I just write down the genus 1 free energy and the genus 0 two-point function. So and you can look in these notes to steps. So I erased the equation, but this was how it looks like. So we need the right-hand side, and that can be computed as follows. So this is universal already. And it's a rational function, as I claimed. So you can write this as the sum of poles of first and second order. Then you need these basis functions. Now I can give you the simplest basis function that looks as follows. Now you can check that applying this integral operator on this function will give 1 over p minus a. This is very similar basis function then for 1 over p minus a squared. That's all you need also for b to invert this right hand side here, and then you get the genus 1 contribution in terms of the basis functions and moments. And if you then do this integration here, what you get is the following. one free energy for arbitrary potential. And A1 and B1 minus 106. And again, this is a universal quantity, and we were decided that this could be done in full generality. So this is not a perturbative expansion, it is an arbitrary potential with arbitrary many couplings, writing the first order correction to the free energy in terms of these parameters. And maybe I should have said, and of course you can then compute them and for, let's say, for a fixed potential of sexty order, so they will be of the form G plus 2 or something plus 2. And if you truncate your potential, then it will be finite number. Okay, I think this is a good point to stop if you want to have a short break. Okay.
Okay.
So I would like to finish off this chapter of loop equations and application to quantum gravity with a few remarks. First of all, there was one question that I think I should have explained better, or where maybe I should make the idea a bit clearer. So the question is, I mean, we made this ansatz of having one cut or two cuts or three, and the question is, I mean, why or when do we take which ansatz? So let's look again at what we had. You remember we solved the quadratic equation of this kind before making this ansatz, and then we thought about, well, what could the solution look like? Now, of course, the ansatz we have to make depends on the potential. So if the potential looks like this, then it's clear the eigenvalues will condense in the minimum of this convex potential. If the potential looks like this, then we have two cuts. If we have this, we can have three cuts. And then, of course, it depends on the parameters. I mean, when we lower this barrier, eventually we will have a phase transition where a zero develops. Here we can also have three cuts, so then if this goes up, we can have a transition like this. So this middle cut will vanish. We can also have this. And this is of course unstable, but we expand it around the larger limit, so if this is deep enough, then this can be filled by eigenvalues, and this is without them spilling over. And when we lower this barriers here, or we put this up, eventually this will fill everything, and this will correspond to the critical points when we don't have the square root here, but 3/2 or 5/1. Okay. Now you also see that, well, when this happens, the stable solution will stop to exist. Like if you had this potential here, you would not have expected any solution at all, right? Because the potential is repelling and there will be no condensation of eigenvalues anywhere. So it's clear that in principle, we would have to make a phase diagram and look at the different regions of coupling constants, and some region will be empty of a solution, some will have a one-cut solution, some will have a two-cut solution, then we will have phase boundaries, so here the one-cut solution would stop to exist. And we would have to then discuss, in case we have a coexistence, let's say between these two, which one has a lower free energy. The free energy you can calculate, you know, it was the integral of the solution of the Self-One equation minus integral rho log. But I will not discuss this in detail because, well, you have to then stick to a specific potential and then discuss the different possibilities, and it gets messy. I prefer to present the general strategy. So this was one remark. Then the second remark was I promised to you that these random matrix models have something to do with conformity theory. And one of the glimpses that you could have that there is indeed a relation was that I claimed that we have some Virasoro constraints hidden in here in this partition function. So let me call the coupling constants in the potential now K rather than K. So I can start from 0. And then, if you remember when we derived the loop equation, in the first step we had done substitution. So we had done this shift h goes to h plus epsilon p minus h, and then we got an equation that eventually, after some massage, gave us the loop equation, and the equation looked like follows: trace 1 over p minus h square minus n. Okay, I can already divide it by n trace 1 over p minus h v h. So that was at the pre-step, the loop equation. Here you see already this gives w of p square plus the connected part, and this then we had to massage a little bit. This gave rise to this complex quantum integral. So let's not do that now. Let's just expand this equation in powers of p, and let's see what we get. So we get the following. Again, I use here the Cauchy product. I mean, these are two infinite sums that you can write as an infinite times a finite sum using the Cauchy product, trace h k minus n minus 1 minus n times minus okay, and this is 0. Now you see if I introduce the following operator, k, as a differential operator, n, such that n plus n is equal to k, plus n from 0, then tn if I let this act on the log of the partition function, or I think the precise statement is the following. So T is the set of coupling constants. So the statement for every power here in the loop equation of order p can be generated by such a differential operator, where you see that if this acts on e to the potential, I hope this is right, this should bring down in power what do we call it, L and M. So the sum of these two powers is always k. I hope I did not make a mistake here. And then this will bring down v prime and some extra power n plus k. So this operator acting on this object here is 0. This is just equivalent to these equations for k equals minus 1, 0, 1. And now you can verify that these LKs satisfy the Virasoro constraint, the Virasoro algebra. So that is the relation between our loop equations expanded in powers of p for large p and generators of the conformal transformations, at least not all of them, but all up from -1, annihilate this. Okay. So I would like to, if you don't have any further questions, I would like to start something new. Well, first of all, I would like to remind you, I mean, we had so far, in the beginning, we looked at this semicircle. Okay. And now we have computed the semicircle, so this was done. But in a way, we took a detour to compute resolvent operators. Okay, so this one, principally you can also compute this one. Now, I would like to go back to this picture here and compute not the limit here where we smooth all these fluctuations here, but where we ask ourselves, can we also say something about local properties of the matrix?
Can I ask you one more question about the previous remark? So I missed, is there a central charge contribution also to this Universality, or is it the classical one?
No, this is the classical one.
So how do you get the extension from this?
Well, you don't see that on the level of loop equations.
Okay.
Okay. And we have, I think we have seen that unless you do fine tuning, C is 0. Okay. So you would. I don't know actually. It's a good question. I mean, I don't have seen. I have not seen loop equations leading to something with a central extension. But it's clear that this is an issue that has to do with double scaling. Okay. And if we don't fine tune, we get C equals 0. Okay. So from these quantities, what we could calculate also higher order density correlation functions like this rho of lambda. This was defined as the limit n of infinity of 1 over n 1 to n delta lambda minus lambda I. Or you can also write this as 1 over n trace delta minus h. And then you can also define higher density correlation functions. Just putting here 2 delta functions. Okay. So then you would get in the large limit, you would get rho of lambda, rho of mu, plus rho connected lambda comma mu, and you would also get a convex term of lambda. Okay. Now these rho of lambdas we calculated using this one. The connected part you can compute from this one, and you also have this one. Now the setup of the loop equations is such that we will only get these smoothed correlation functions. Okay, they are also called macroscopic, smooth, or wide, or macroscopic correlated. And the reason why we were interested in this was that we actually set up a counting problem and this application to 2D quantum gravity that we wanted to solve, and this matrix model calculation was a way to solve this counting problem. Now, I want to go back to the very first pictures I showed and show you another technique to solve matrix models and also to get to this application to QCD. So what we will be interested in there is we will actually zoom into this neighborhood or this neighborhood and with a kind of magnifying glass. And I showed you already what comes out here. There comes out tracy rhythm. This I will not have time to derive. So we will look at this, if you like, the fluctuations the larger limit around this semicircle or not semicircle density. So it's a different larger limit, and as you will see, I mean, there are many larger limits you can take in matrix models, depending on which question you ask. So this was one question we asked, now we will ask a different question. And also the answer to this question will be universal. But it's a different universality. It will be called microscopic, because one could take a microscope and zoom in. And I think most of the applications that I showed to you, like the Riemann zeta function or the QCD smallest eigenvalue, they were of this microscopic type. So what I will do now is I will go back, start again from scratch. Now I will start from the eigenvalue picture, and I will show you a way to solve matrix models actually at finite n without approximation. And that will occupy us for some time. Okay, so. So what I would like to do is the following: matrix models using orthogonal polynomials. And this will lead to microscopic, if we do the right unit and ultimately the application QCD. But first we have to go back to the matrix model and try to solve that for finite n. So exact solution n finite. Okay. So because I will focus on this QCD application. You remember we had this chiral symmetry. We had this chiral Dirac operator. So we had the partition function. In terms of eigenvalues, okay, the constant was not so important. One to n d number I, and we have here some power. And we had a one-on-one determinant of beta equals 1, 2, and 4. So if you want, you can keep this as a concrete example in mind. So if you call this alpha, you will see, this is the weight function for Lagrange polynomials. And what I will say in the following will be mostly true for the generic weight functions. And at some point, we will have to come back to this particular example. But you see already, it may be a good idea to make Lagrange polynomials appear here because they are orthogonal with respect to this weight from 0, 1. Okay. So before we do that, I would like to define again what the objects are that we are interested in. And these are the k-point density correlation functions. So I will denote them n beta. So they depend on k eigenvalues. We have some normalization here. That is tradition imposed. And then we integrate the whole integrand not over all eigenvalues, but over n minus k. out. So the density, for example, R1 number 1 is just the integral over the number 2 by 2. Okay, and of course you can get this integral by doing this delta lambda 1 minus lambda, and then of course you have to use that the integrand here that is also often called joint probability distribution function. So that depends on eigenvalue is invariant under Hamiltonian or eigenvalues. So so this is what we call rho, actually rho n. However, I would like to point out that this definition is slightly different because we will never have contact terms. The 2-point function is integrating our 2 eigenvalues, but we don't put delta function. We just leave the integral over 2 eigenvalues. So these Rn's will give rise to the same object as we have here, except the contact term. And this is just a matter of notation, but I don't want you to get confused about this. So, as I already said, it will be useful to introduce polynomials that are orthogonal with respect to the way that we have them. So let me write down what that is. So we are after the following objects. So let me call orthogonal polynomials P. Lambda, lambda, and I'll put here twiddle, which will soon go. So these are in monic normalization. First order lambda minus 1. And then of course P k divided by the square root of the norms are orthonormal. And I do that now for arbitrary weight functions, so this can also be GUE, so just e to the minus lambda squared integrated over the full width. Okay, and of course these h's are the norms squared. Okay, now why is it useful to introduce these? Well, this will be only useful for beta equals 2. So in the following we will mostly consider beta equals 2 was complex Hermitian matrices. Here power was 2. The same setup can be done also for beta equals 1 and 4. But we will need something more complicated. So we need a different scalar product basically. So this is a scalar product. Okay. And there we will need anti-symmetric skew symmetric scalar product, which is not quite definite. I will give some remarks at some points, but this, because this procedure is a bit more complicated, I will not give so many details. Now, the fortunate thing is that the symmetry class where 3-color QCD sits in is the beta equals 1 class. So fortunately there the calculations are the simplest, and that's why I think it's good that I will present those. So, what is the idea that we will apply? Or maybe let me give two examples. So, e.g. W square on R, then we have that Pn will of lambda just 2 minus n h lambda. Likewise, you can see that the Mie polynomials, the Laguerre polynomials are orthogonal polynomials with respect to this measure here on R plus. So what is the idea? So the idea is very simple. Basically, we will do linear algebra on the Vandermonde determinant. Okay, so what was the Vandermonde determinant? This was product minus j lambda j minus lambda I. So I'll just take one of them at the moment. Okay, we have two, so we can choose two. Now, I already wrote down that this is also equivalent to lambda I to the power j minus 1 for this. So let's write this up as a determinant. Lambda 1 square, lambda 1, n minus 1. 2, n. Now we do a very simple trick. As you know, the value of the determinant does not change when I add rows to each other or columns to each other. Okay, so I can add multiples of all the columns on the left to the last column and generate an arbitrary polynomial here of degree n minus 1 without changing the value of the determinant. So I get here q degree n minus 1 of lambda 1 up to q n minus 1 lambda n. I can continue and I can get arbitrary polynomials here, so I get q0 lambda 1, q1 lambda 1, etc. Okay, this is still an identity. Now, you can already see it is probably a good idea to choose qk of lambda orthogonal with respect to this weight, because then we do that with both determinants. So then we have one determinant of p's times the second determinant of p's, and if we then expand the determinants in the Laplace expansion, we can use heavily this orthogonality. So then many of the terms in this integral will actually vanish due to orthogonality. That's why it is a good idea. And it's also a good idea if we want to compute correlation functions, because, because these n-fold integrals or n minus k-fold integrals, and please remind yourself that at the end we do want to take the limit n goes to infinity. This would drastically simplify. So that is the idea of this approach. Okay, so as the first and maybe last step for this morning session, I would like to show you how to compute the partition function now in terms of these polynomials and their square norms. Okay, so let's go for that. So we just play a trick, a little bit of linear algebra and combinatorics. So let's do the following. So the partition function is written as constant times 1 to n w d lambda I w lambda I. Now I take beta equals 2 here. Okay. So I can drop the absolute values. So I take one determinant of polynomials p, Laplace expanded, and multiplied with the second one, also Laplace expanded. So these are now permutations. This is the sign of the permutation of sigma and sigma n. So the first one Lamont determinant will give us the following. Okay. Sigma 1 minus 1 lambda 1. Sigma n minus 1 lambda n. I have a minus 1 here because, you know, I mean, the degree of the polynomial starts with 0. So the 0th polynomial is just 1. Okay? Going up to n minus 1. That's why I put here minus 1. And it's just a matter of notation. And I think I've not been consistent here. So this was the first one Lamont, some of our permutations. The second one Lamont is just a line. Sigma prime 1 minus 1 lambda 1 en sigma n prime minus 1 lambda n. Okay, now we can do the integrals. So we integrate over lambda 1, so we have to pair this one with that one. Obviously, this will only give a contribution when the indices here are the same. So I get delta sigma 1 prime sigma 1 times the norm h sigma 1. Okay. Then I continue with all these blah 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 until I get here. So what do I get? I get, because of all the deltas, one of the sum of our permutations will be killed. The signs will be the same, so that's a plus. So I get one sum of permutations left, and then I have a product I from 1 to n h. Sorry, there should be minus 1. And of course, I drop the minus 1 on both sides. Okay, sigma I minus 1. Okay, but now you see this product here, it's always the product of all norms, or squared norms. Okay, so this is actually, I can reorder them. So this is just, okay, then you write an equation. Constant sum of our permutations. J from, let's write it now properly. Okay, because all products, all factors will appear exactly once, so I can order them the proper way. And of course, this I can take out of the permutation. And what I get is, well, the permutation just gives n factorial. Okay? So our result is z and beta equals 2 is some constant that will drop out anyway in expectation values that we consider times n factorial times the product of the norms of these polynomials. Okay. So in the following, I will very often drop this out, and I was, I think I forgot the definition of the Akemann function. Did I put the 1 over z as the normalization? Please have a look. I mean, it's in here. First, we have to normalize. Okay, so in the
date point density function. It was a 1 over z.
There was a 1 over z. Okay, good. Because I was not sure. Because if there's 1 over z, this constant will drop out with the constant that we have. So in the future, basically all that we need to know is this one. Because this was just factor 2 in the volume of the unitary group that we don't need to know. Okay. So, maybe I should make one more remark and then let you have a break for the next lecture. Okay, so the polynomials that I have written down here, they are of course only known explicitly for few cases. Okay, so for Gauss, I could write it down as Hermite, or for Laguerre weight, I could write it down as explicitly. However, in general, it can be constructed in two different ways. So one way you probably know from your analysis or linear algebra, which is a Gram-Schmidt. And that is, okay, I think I will space. So the monic polynomial of degree k of lambda is given as follows. You can construct it in terms of the following determinant, lambda squared, lambda k. And the remaining points you have to put in here are the moments. So we have to put here m0, m1, m2, m1, m2, etc. And mk are just the moments with respect to the wave function. Okay. So you will see that the last moment here is in k. These are k plus 1 terms. Okay, 1 to lambda k. This will be a polynomial of degree k. And here the last term will be m to k minus 1. And I have to normalize this with some determinant ck. And that is given by m naught to k minus 1. And that's also determinant m a plus b, where these run from a to minus 1. Okay, and this is a special case of what is called a Hankel determinant. And that is when the determinant here is just depending on something where the indices are a plus b. And this case, and there's also something just so that you know the name, just this determinant. This one also. This is one way to characterize these orthogonal polynomials. However, this is not the way we will look at them. There's a second way that is recursive. So you start with polynomial, let's say lambda 0, and then you express them successively by the next. This is the one way we will use, and so this afternoon I will start to compute properties of these orthogonal polynomials. Much of this work is really classical analysis, but some works are very new. And we will then manage to compute all Akemann density correlation functions in terms of, we can do all the integrals, all with n minus 1. Then we will get some kernel of these polynomials, and then we will have to analyze the symptotics of